So hi everybody, my name is Arie Staal. So I'm a postdoc here at SRC, but what I'll be presenting is mostly a result from my PhD studies at Wageningen University in the Netherlands about tipping points in the Amazon, ecological biophysical tipping points. So in that sense there is a bit of an overlap thematically with what Carlos Nobre has been presenting and also a bit with what Lan Wang Erlandsson did, but I think it's complementary to these previous talks. When we talk about tipping points in the Amazon, I think we should consider at least two scales at which processes operate. First, there's a local scale at which tipping of the forest might occur, and there is the more regional scale dynamics of moisture recirculation that was the topic of the previous talk. So to start with a more local scale. So when we look to the distribution of tree cover per unit of area, then there's a large range of climatic conditions, of rainfall conditions where tree cover distribution is bimodal. So either we find high tree cover, the forest, or very low tree cover, which is the savanna. And these intermediate values of 50% tree cover are very rare. And the fact that external conditions cannot fully explain which ecosystem type we find is an indication of that these forests and savannas can be alternative stable states with the possibility of tipping. So that is illustrated in this diagram that is constructed using tree cover distributions, empirical tree cover distributions from across the tropics. And here the ecosystem state is represented by a ball. Also we've seen it in Chandrakant's and Carlos's talks that can move around in a valley, and under certain conditions, certain rainfall levels, the ball can be in either of two valleys in the landscape, two alternative stable states in which it remains. And this suggests, this implies that tipping points might occur, and there's basically two types of ways in which that might happen. First of all, if the conditions change, for instance the climate changes, then the landscape in which the ball moves around itself changes. So the stability of the forest might decrease, and then the ball sort of by itself, so to speak, rolls down a hill into the state of low tree cover and remains locked there. Alternatively, the landscape remains the same, but the forest is disturbed and the ball is being pushed around, so to say, and then it's pushed across a threshold into the state of low tree cover. So these are the two types. Then the question is, what mechanism might cause such behavior? And also what came up in the talk by Carlos Nobre is a main suspect that has been identified in a range of studies is fire, or more specifically a feedback between fire and tree cover. These fires mainly occur in savannas, in grasslands, where the grasses are easily ignitable, they burn much more easily, and the fires keep the landscape open by killing trees, for instance, and once there is a forest, then the grasses are suppressed, so there's fewer easily ignitable fuel load, and beneath the canopy a humid microclimate also suppresses fire. So these are dynamics on a local scale that may make a forest tip. But the part of the Amazon that is potentially susceptible to this kind of tipping is very large. So it's anything but the dark green area. This is a map that was constructed based on the relationship between climatic variables and tree cover distributions. So large parts of the Amazon are potentially already under current conditions susceptible to this kind of phenomenon. So apart from this local behavior, there is the more regional scale moisture recirculation that Lan talked about. So the trees in the Amazon, they take up groundwater from deeper groundwater layers and they release it to the atmosphere when they photosynthesize, what is called transpiration. So they enhance the evaporation across the Amazon, in which it can, well, stabilize the forest again, potentially. So what we did is we looked at this phenomenon by modeling the contribution of the forest to evaporation and simulating where that water rains down again and how it affects the resilience of those forests. So what we see here is the transpiration of trees in South America that actually rains down again on the land. And on the continental scale, the Amazon, a large part of the Amazon stand out. And here we plotted the distance that the water after its evaporation, after transpiration from the forest, travels through the atmosphere before it rains down again, and that's about 600 kilometers median for the Amazon. And this is the fraction of rainfall on an annual level that has been transpired by trees in the Amazon. So we see that especially in the southwestern part of the basin, up to half of the rainfall is due to the fact that the forests in the Amazon take up this deeper groundwater and release it to the atmosphere. But apart from the spatial difference, we found temporal differences. So what's plotted here on the x-axis is the amount of moisture that enters the Amazon basin from the ocean. And on the y-axis is the contribution of this forest transpiration to rainfall in the Amazon. So we see that the drier it gets, the more important the Amazon becomes for its own rainfall. So this is between years, but we saw a similar pattern between months. Here again, for individual months, less rainfall that enters the basin from the ocean, the more the forest contributes to its own rainfall. So that's a self-stabilizing mechanism that might be disrupted if deforestation occurs, if parts of the forest are lost. So we looked a little bit more into that, using these methods to use tree cover distributions to assess the resilience, the stability of the forest. And here we see that the dependency of the forest, or forest resilience, forest stability, on the moisture that has been transpired by trees in the Amazon. So also here, not surprisingly, we see the southwestern Amazon standing out. So these are very dependent on forest upwind for their stability. And this method also allowed us to turn the question around and ask which forests are so important for maintaining the stability of these vulnerable forests, mainly in the southwest. So we assign a weight to the molecules that evaporate, that transpire from the trees, based on the stability of the forest where it rains down again. And then we see a bit of a different pattern emerging, where basically the southern half of the Amazon, the transpiration from the forest there is critical for maintaining the stability of the vulnerable parts of the Amazon. This does not mean that the forests in the northern half do not contribute to rainfall a lot, because they do. But it's mainly because we assigned large weights to the southwestern parts of the basin that this pattern emerges. And this is very relevant because deforestation mainly occurs in the southern part of the Amazon and the eastern part of the Amazon. And it also highlights, also as in line with what Lan explained, the international effects of deforestation, because deforestation in Brazil has implications for the stability of parts of the forests in the southwest, which is where Bolivia and Peru are. And that was basically my story for now, because deforestation is a topic of further presentations also later. So, Thank you very much.